Video number 4, where we're going to look at positron decay. And this is the fourth possible option that an unstable nucleus could take in order to become stable again. So in this example, I've used an atom of helium as our start point, as our unstable nucleus. So this atom of helium has an A of 4. It's got 4 particles in the nucleus, or subatomic particles in the nucleus, and it's got a Z, an atomic number of 2. That tells us that of those 4 particles in the nucleus, 2 of them are positive protons, and we can see that down here. We've got our 1, 2, 3, 4 particles in the nucleus, and 2 of them, 1, 2, are positive protons. And at the moment, this nucleus is unstable, meaning that strong nuclear force that holds this nucleus together isn't quite strong enough to overcome the fact that these 2 protons want to push away from each other. So we have got an unstable nucleus. But the nucleus can do something about that. It can decay via positron decay. That's one of its options in order to become stable again. So what is positron decay? This is one of those transformer examples, but this time in positron decay, this is when a proton, that we can see here, I've circled it in green, a proton transforms into a neutron. So we have one of those transformations. A proton becomes a neutron, it changes its identity. And as it does that, it emits, it kicks out a little positron. Hence, positron decay. And a positron is just like an electron in that it has virtually no mass, but it does have a positive charge, whereas electrons had negative charge. So that is what a positron is. And in this example, when the proton turns into a neutron, it emits a positron at the same time, and what is left behind is a nice stable nucleus over here. So let's look at exactly what has been left behind in our stable nucleus. To count up the number of subatomic particles in the nucleus, we've got 1, 2, 3, and 4. So it still has an A, a mass number of 4, but now we have a difference in that there is only 1 proton left because this proton turned into a neutron. So we've only got 1 proton left. So we need to change that Z, that atomic number, down to 1. And because the atomic number, the number of protons, has changed, that must mean that the identity of the atom has changed too, because it is the number of protons that controls the identity of an atom. So now, if we were to look up on a periodic table, which is the element with an atomic number of 1, we would find that it's now hydrogen. So it's changed its identity, and we now have a stable hydrogen atom. If we were to put that back into our equations like we always do, we started out with our unstable helium nucleus or helium atom with a mass number of 4 and a proton number, an atomic number of 2. We emitted a positron, and we write that as an E because it's like an electron with no mass, but it has a positive charge, a positive electron, a positron. And just like we wrote down here, we were left with an atom with 4 subatomic particles in the nucleus, 1, 2, 3, 4, and just one of them is a proton. That means we're left with hydrogen. Lastly, if we're to look in terms of the general equation, we always talk in terms of our unstable atom being letter X with A as its mass number and Z as its atomic number. We show that a positron has been emitted, so we have that E with no mass but a positive charge. And what's left behind? Well, we can see that the A is not changing. The mass number is not changing. The number of subatomic particles in the nucleus does not change, 4 to 4. But what has changed is the Z, the number of protons. And the Z has gone down by 1. We had 2 over here, we've now only got 1. So we say it's Z minus 1. And because the Z has changed. We can no longer say that the element identity is X. It's changed now. It's become something different. So we must put letter Y here. Okay, that is positron decay. Little positron, I hope you found that helpful.